Reciprocity is an important evolutionary human development, originally conceived by Trivers. Drawing on such anthropological studies, Kim Hill has suggested that human cooperation based around reciprocity involves three evolved predispositions. First, there is a predisposition to seek cooperative solutions that will benefit all parties relative to non-cooperators. Second, a predisposition to share cooperatively acquired resources with all of those deemed to belong to the same group. And third, a predisposition to punish non-reciprocators even if the punishment is costly. Today, most social scientists would agree that humans do engage in acts of reciprocal aid. The only debate is whether this is due to evolved predispositions or a cultural invention in each society. Reciprocal back-scratching appears to be rife across widely separated human cultures, although the precise form that it takes may be related to economic factors specific to a given society. Clearly, since everybody in the group will benefit, cooperating makes sense, or does it? During the middle years of the 20th century, a number of mathematicians suggested that cooperation might not make sense. They based this argument on a game.
Back in the 1970s, an unexpected breakthrough was made by a mathematician named John Conway, here in Cambridge. He devised something called the game of life, a simple simulation that shows how a complex thing like the mind might come about from a basic set of rules. The simulation consists of a grid, a bit like a chessboard, extending infinitely in all directions. Each square of the grid can either be lit up, which he called alive, or dark, which he called dead. Whether a given square is dead or alive depends on what is happening in the 8 other squares that surround it. For example, if a living square like this one has no living squares nearby, the rules say it will die of loneliness. If a living square is surrounded by more than 3 other living squares, the square will also die of overcrowding. But if a dead square is surrounded by 3 living squares, it becomes lit, or is born. Once you set an initial state of living squares and let the simulation run, these simple laws determine what happens in the future. The results are surprising. As the program progresses, shapes appear and disappear spontaneously. Collections of shapes move across the grid, bouncing off one another. There are whole kinds of objects, species, that interact. Some can even reproduce, just as life does in the real world. These complex properties emerge from simple laws that contain no concepts like movement or reproduction. It's possible to imagine that something like the game of life, with only a few basic laws, might produce highly complex features. Perhaps even intelligence. It might take a grid with many billions of squares, but that's not surprising. We have many hundreds of billions of cells in our brains.
There is a branch of mathematics that deals with the decisions that people are predicted to make depending on the strategies of others. It's called game theory. The whole idea about game theory is that it examines problems the world presents in both simplified and universal ways. One of the main aims of game theory is to find a solution to a problem which, given what everybody else is doing, cannot be bettered. This is known as the Nash equilibrium, after the Nobel Prize-winning Princeton mathematician John Nash, about whom the film A Beautiful Mind was made.
Incoming, gentlemen.
Aye, aye. Deep breaths. Nash, you might want to stop shuffling your papers for 5 seconds.
I will not buy you gentlemen beer.
Oh, we're not here for beer, my friend.
Oh. Does anyone else feel she should be moving in slow motion?
Will she want a large wedding, you think?
Should we say swords, gentlemen? Pistols at dawn?
Have you remembered nothing? Recall the lessons of Adam Smith, the father of modern economics.
In competition, individual ambition serves the common good.
Exactly.
Every man for himself, gentlemen.
And those who strike out are stuck with their friends.
I'm not gonna strike out.
You can lead a blonde to water, but you can't make her drink.
I don't think he said that.
All right, nobody move. She's looking over here. Right, she's looking at Nash.
Oh, God. All right, he may have the upper hand now, but wait until he opens his mouth. Remember the last time?
Oh, yes, that was one of the history books.
Adam Smith needs revision.
What are you talking about?
If we all go for the blonde, we block each other. Not a single one of us is going to get her. So then we go for her friends. But they will all give us the cold shoulder because nobody likes to be second choice. But what if no one goes for the blonde? We don't get in each other's way, and we don't insult the other girls. That's the only way we win. That's the only way we all get laid. Adam Smith said, the best result comes from everyone in the group doing what's best for himself, right? That's what he said, that's right? Incomplete. Incomplete. Okay? Because the best result would come from everyone in the group doing what's best for himself and the group.
Ash, this is some way for you to get the blonde on your own. You can go to hell.
Governing dynamics, gentlemen. Governing dynamics. Adam Smith. What's wrong?
Yep, here we go.
Careful, careful.
Thank you.
Having been developed by economists to predict what people are likely to do with investment decisions, John Maynard Smith introduced game theory into animal behavior to explain the relationship between behavior and evolution. Subsequently, it has been developed to help understand the evolutionary basis of human decision-making. One particular hypothetical scenario that game theory has been applied to solving is called the prisoner's dilemma, and it has some interesting parallels with reciprocity. In the prisoner's dilemma, two criminal suspects are arrested by the police and placed in separate questioning cells. As you learn about this game, think about what you would do if you were playing it. Also, think about how this game might parallel other real-world scenarios you've been through. Each is told that if they implicate the other, they will be rewarded and set free, while the other will receive a harsh sentence. If, however, neither talks, then both will receive a light sentence. In game theory terminology, implicating the other is called defection. The refusing to talk is called cooperation. The outcome or payoff for each player is generally symbolized by one of four symbols. T is the temptation to defect. R is the reward each receives if they cooperate. P is the punishment they receive if both defect. And S is the sucker's payoff, that is, if you cooperate when your partner has defected. In this setup, it is important that the payoff decreases from T through R and P to S. Mathematically, we can express the payoff in the prisoner's dilemma as T greater than R greater than P greater than S. In practice, the game is played for points. Typically, the following values are given: T equal 5, R equal 3, P equal 1, S equals 0. This makes sense when we consider that T has to involve a temptation, signified by that it is the biggest individual payoff, but only if the other party does not defect, which leads to the P payoff, the second smallest payoff. It is also necessary that the combined payoff for mutual cooperation, R equals 3 times 2, which equals 6, is greater than the combined payoff for cooperation and defection, which equals 5 plus 0 equals 5, since otherwise there is no real incentive to cooperate. Here's the dilemma. Both players should realize that rationally they should defect, even though this makes each worse off than if they both cooperated. Since if you are playing this game, you must consider what your partner might do. If your partner cooperates, then by defecting you will gain 5 points. If your partner defects, then you will have to defect in order to gain the 1 point for punishment, rather than the 0 that is the sucker's payoff. The dilemma comes down to the fact that you do not know what your partner is going to do. So you'll get either 3 or a 0 by cooperating, but a 5 or a 1 for defecting. Therefore, the prisoner's dilemma basically suggests that people should not cooperate. Of course, the prisoner's dilemma is just a theoretical game. However, prisoner's dilemmas emerge all around us in our social interactions. You may have heard the phrase tragedy of the commons. In fact, it describes one possible outcome of the prisoner's dilemma. As Matt Ridley puts it, broadly speaking, any situation in which you are tempted to do something, but know it would be a great mistake if everybody else did the same thing, is likely to be a prisoner's dilemma. Thus, deciding whether or not to buy a round of drinks, deciding whether or not to repay the favor of babysitting, considering the tipping of a waiter, and perhaps most importantly of all, deciding whether or not to remain faithful in a relationship. These may all be thought of as the equivalent of prisoner's dilemmas. The dilemma that players face lies in deciding whether to reciprocate or to cheat. If, as Ridley claims, prisoner's dilemmas are all around us, and if the only logical act is to cheat, then how can we explain the regular reciprocation that we encounter in human societies? The same problem occurred to students of economics before Trivers had even proposed reciprocal altruism. Many claim that we should not expect to see cooperation under such circumstances, and yet, all around us, people are cooperating. The mathematicians who initially explored the prisoner's dilemma in the 1960s also found that people often cooperated in the game even though this seemed illogical. They concluded that people are not behaving rationally, that they weren't sophisticated enough to realize that mutual defection is the only logical response. But if the prisoner's dilemma is a model of the sort of decisions we face all the time, then surely we should have evolved a psychological predisposition to play the game rationally, right? The answer came when animal behaviorists pointed out that real-life social relations are rarely like a one-off game of prisoner's dilemma, but that social animals encounter each other repeatedly and remember what happened on the last encounter. So social life is more like a series of prisoner's dilemmas where the same players meet each other frequently, and therefore have some idea of whether the other players might cooperate or defect. In one-shot prisoner's dilemmas, defection is the only logical option, but when the game is played repeatedly by the same two players, called Iterated prisoner's dilemma, they will frequently fall into a pattern of mutual cooperation. In this way, both players will continually gain the 3 points. When this is compared with the average score that is achieved via a mixture of the other 3 outcomes, both players will have a better overall score. When you have reasonable confidence that your partner will not betray you, then the lower reward of 3 points per game seems a lot better than having a chance to get 5 points, 1 point, or no points. In this scenario, where players can form long-standing alliances, the average reward for cooperating is 3, and the average reward for defecting is 2. The rationality of mutual cooperation in this scenario even stands up to the test of computers. When different computer programs are played against each other, typically the winner is one called Tit-for-Tat. In Tit-for-Tat, the strategy is to cooperate on the first move and thereafter do whatever your opponent did on their last move. Complex programs have been written involving a number of contingent rules, depending on what your opponent does, and that may involve switching strategies suddenly. But on average, TFT still always wins, even against the most complex strategies. This may help to explain why people often try to cooperate, even in one-shot games of Prisoner's Dilemma. They and their ancestors were unlikely to find themselves in positions where their social behavior has no possible future repercussions. So they may have evolved an emotional, instinctual predisposition to cooperate. Rather than evolving the neural circuitry to logically determine that cooperation is usually beneficial, we've simply evolved a natural tendency to cooperate by default. Although it produces worse results than a computer in those rare situations where we can't influence each other's behavior, this kind of innate tendency might be more likely than pure logic for natural selection to stumble upon, and it was clearly adequate to promote the formation of massive human civilizations. So why exactly is Tit-for-Tat so successful against all other strategies? Political scientist Robert Axelrod, who has been at the forefront of examining Prisoner's Dilemma, considers TFT to be an evolutionary stable strategy, or ESS. An ESS is a strategy that will never be replaced by another strategy once enough members of a group adopt it. Axelrod believes that Tit-for-Tat is an ESS because it has 3 strengths. It is nice. It never defects first, which means it encourages cooperation. It is retaliatory. Defection occurs immediately after the opponent has defected. It is forgiving. If a previously defecting opponent then cooperates, it will immediately also cooperate. All of these attributes produce a very predictable strategy, so anyone employing this strategy appears trustworthy. If someone never defects first and always reciprocates or retaliates in response to your actions, then you have a strong incentive to cooperate with this person and begin employing the same strategy. According to game theory, soon enough the strategy will spread, societies will form, and eventually Tit-for-Tat will form the basis for legal systems. Today, many social scientists believe that Tit-for-Tat describes a common strategy that people employ when deciding how to respond to others. In addition to helping to describe and explain general incidents of social responses, it has even been used to help explain behavior during warfare, both for the escalation of violence and in some cases its dissipation. You might be surprised to hear that a TFT strategy can lead to reductions in violence during human warfare. Most soldiers do not have the repeated contact with individual members of the opposing army to allow for a positive tit-for-tat to develop. However, during the trench warfare of the First World War, company units faced each other over no man's land for lengthy periods of stalemate. Frequently, during these encounters, it became obvious that troops were beginning to fire over the heads of their opponents. Once such a gesture was made, reciprocal shoot-to-miss strategies were very quickly set up. Both sides realized that they were encountering the same individuals repeatedly, which meant that they were in a position to remember the previous actions of their combatants. So individuals of both sides would be better off by cooperating. On occasions when the unwritten shoot-to-miss agreement was broken, retribution was always swift. Typically, the number killed would also be killed by the opposition. Likewise, a return to restraint was met with reciprocity. The behavior of troops under such conditions is eerily similar to the behavior of the Iterated Prisoner's Dilemma computer program designed to play with a tit-for-tat strategy. Sadly, when the senior officers eventually realized what was happening, they began to move units around so they couldn't develop relationships with the opponents, and started up raiding parties, both of which strategies put an end to what might have developed into a relatively painless war.